Welcome to the Lab of Life, everyone. Today's explainer is all about unlocking the secrets behind one of the absolute most fundamental, yet completely invisible chemical processes happening all around us literally right now. We're talking about diffusion. Whether you're gearing up for your IGCSE exams or you're just super curious about how the physical world actually works, you are definitely in the right place. So let's jump straight in.
To kick things off, let's ground this abstract science in something we've all experienced. Have you ever noticed how the amazing smell of whatever's cooking in the kitchen reaches you way before the actual food does? Or think about someone standing all the way across the room and they give a quick little spritz of perfume. Within seconds, even though you are absolutely nowhere near them, you smell it perfectly. How exactly did those completely invisible scent particles travel across that empty space to reach your nose? Well, that's exactly the mystery we're solving today.
Here's our syllabus for today's session. First, we'll look at the invisible spreading force. Then, we'll clearly define what is diffusion. After that, it's a showdown between gases versus liquids, followed by the variables for speeding up the process. And finally, we'll look at how this is literally keeping us alive.
All right, part one, the invisible spreading force. Let's get right to it.
Okay, let's dive into the actual mechanics behind those everyday observations, like that perfume spreading across the room. If there's one single thing you commit to memory today, make it this golden IGCSE definition. Diffusion is the net movement of particles from a region of higher concentration to a region of lower concentration, entirely due to their random motion. Let me break that down. Put incredibly simply, particles naturally want to move away from areas where there are tons of them all crammed together, and they want to spread out into areas where there's more space, where there are fewer of them, from high concentration to low concentration. It's really that elegant.
Moving on to part two, what is diffusion? Let's zoom in a bit closer.
Now that we've got the textbook definition down, we need to see exactly what's going on with these little particles at a microscopic level. Because remember, there isn't a fan blowing them and there's no tiny motor pushing them along. So why are they moving at all? Well, this brilliantly illustrates the step-by-step process. Step one is the engine of the whole thing. Particles possess kinetic energy. Because they have this energy, they're in continuous motion. Step two shows us that this movement is completely random. They're just zipping and bouncing around in all directions. Now, step three is where the real magic happens. Because of all this random bouncing, particles naturally end up spilling over into the empty spaces, the areas with fewer particles. And finally, step four. Over time, because they just keep bouncing into empty space, the particles end up perfectly evenly distributed. It's a completely natural, unforced process, driven entirely by their own kinetic energy. How cool is that?
Section 3. Gases versus liquids. Time for a little state of matter face-off.
So we know how diffusion works, but does it behave the same way in every environment? Not at all. When we compare states of matter, we see a massive difference. Take a gas, for example. In a gas, diffusion is incredibly fast. Why? Because the particles are far apart, they're moving rapidly, and they bump into each other way less often, fewer collisions to slow them down. Think about that perfume spreading through the air, or the rapid gas exchange happening right now inside your own lungs. Now, compare that to a liquid. In a liquid, the particles are physically much closer together, so their movement is totally restricted. That makes the whole process of diffusion significantly slower. If you've ever dropped a tea bag into hot water and watched the colors slowly spread, you know exactly what I mean. It just takes more time.
All right, section 4, speeding up the process. Let's look at the variables.
Now you might be wondering, if diffusion is just this natural random occurrence, are there ways we can actually manipulate it? Are there specific cheat codes we can use to speed up the universe's natural tendency to spread things out? Absolutely. There are three main factors that affect the rate of diffusion. First up, higher temperature. When you heat things up, you're literally giving the particles more kinetic energy. More energy means they move faster, so diffusion happens quicker. That's why food coloring will bloom way faster in a beaker of boiling water than in an ice bath. Factor 2, a larger concentration difference. If you've got a massive crammed crowd of particles in one tiny spot and absolutely zero right next to it, that initial outward spread is going to be incredibly rapid. But as things start to even out, the rate naturally slows down. And factor 3, smaller particle size. Tiny particles simply navigate and move through spaces way more easily than large, bulky ones. Tiny hydrogen gas molecules, for instance, they're going to zip around and diffuse much, much faster than heavier, clunkier molecules.
Now, what's really interesting is how a classic classroom lab report proves all of this. Imagine dropping a single potassium manganate 7 crystal into a beaker of water. At 0 minutes, it's just sitting there at the bottom. Fast forward to 5 minutes, and this vivid purple color starts blooming from the crystal. At 15 minutes, the color has spread way further. And by 30 minutes, the entire beaker of water is completely uniformly purple.
And the absolutely crucial detail to remember here, there was zero stirring. Literally no one touched the beaker. This timeline is the ultimate, undeniable proof that particles are constantly moving all on their own, driven by kinetic energy, moving from that highly concentrated crystal out into the lower concentration of the clear water.
Bringing us to Section 5, keeping us alive. Let's look at the biological stakes.
Let's zoom way out from that microscopic beaker and look at the real-world stakes here. Because, guys, diffusion isn't just some neat little trick for your chemistry exams. It's the fundamental process literally keeping you breathing as you watch this explainer. Check out this beautiful biological symmetry between humans and plants. Look at human lungs first. Right now in your chest, oxygen is naturally diffusing from the higher concentration in your lungs straight into your blood. At the exact same time, carbon dioxide is diffusing from the higher concentration in your blood back into your lungs so you can exhale it. Now, look at plants. They rely on the exact same chemical process, just in reverse. Carbon dioxide diffuses into their leaves for photosynthesis, and the oxygen they produce diffuses right out into the atmosphere. Humans and plants are both entirely dependent on the invisible, random movement of particles just to stay alive. It's honestly mind-blowing.
All right, let's do a quick recap of our essential lab notes to make sure you're totally prepped to tackle those common exam questions. Remember these 5 core takeaways. Number 1, diffusion is always a net movement from high to low concentration. 2, it's driven entirely by random kinetic motion. 3, it happens in both gases and liquids, though way faster in gases. 4, you can speed the whole thing up with high heat, a large concentration difference, or smaller particle size. And 5, it is absolutely vital for sustaining life.
So the crucial point I want you to cement into your memory is this master definition. If you ever face a question asking, what is diffusion or why does diffusion occur, this right here is your anchor. Net movement of particles from a region of higher concentration to a region of lower concentration. Lock that phrase in, understand the examples we walked through today, and you are absolutely going to crush this topic for sure.
Which brings us to the end of our explainer. But before we wrap up, I want to leave you with one final, provocative thought to ponder. If particles literally never ever stop moving, where is the invisible chemistry of diffusion actively at work around you right at this very moment? Is it the steam rolling off your cup of coffee? Maybe the scent of rain drifting through an open window? Once you truly understand diffusion, it's like a whole new world opens up. You start seeing it everywhere. Thank you so much for hanging out and unlocking these concepts with me today. Keep observing, keep learning, and I will catch you in the next explainer.